So good morning to all of you. So we are going to have our next lecture of analytical and computational methods in electromagnetics. So yesterday we were discussing about the problem of strip line, that is strip line, microstrip line we were discussing. So what we did in the yesterday. So we have a strip line. So a strip line, and was our center conductor, and it was A, it was B, and that is it was V equals to V naught, and its width was W, and on all the peripheries we are having the zero voltage. Now what we want to solve, so we have solved it, that is V of xy at we have solved it. What is the voltage across each and every point on this in this region? So what we did, we have divided these things into a we have used the symmetrical property. So we have divided here like this. So we have divided and we have divided. So and we have taken a one quadrant of it. So what was our one quadrant? Our one quadrant looks like something like this. So it was and we have kept our axis here. So it was x here, it was y, so it was minus b by 2, a by 2, and so where was our conductor? Conductor was here and here only, here and here. So here the voltage was 0 and voltage was V naught. So we have used the series expansion method to try to find out the voltage in the regions. So we have taken two regions, that is region 1 and region 2, and we have expressed, or we will be able to find out the voltage in region 1 and region 2 that we did in the last class. So what was our V1 of x for region 1? Xy was our V naught plus 2V naught B over Y, and our V2 was V2 of xy. V2 of xy was summation n equals to 1, 3, 5. That is odd terms. We will have an sine of n pi y by b sine hyperbolic pi n pi a by 2 minus x over b. Okay, and we have calculated the an. So an was by applying the boundary condition at the interface of two regions, that is region 1 and region 2. So we have calculated it. So what we got? We got an, where an was our minus 8 V naught sine n pi by 2 over n square pi square sine hyperbolic n pi by a minus w over 2b. So this was the expressions we have. And after that, after knowing the voltage in the region and region, that is in the region 1 and 2, what we have asked? We have asked to find out the capacitance per unit length. So that is capacitance per unit length C of the strip line. That was decided that we want to calculate, and we have linked it with the energy stored per unit length. So as we told you earlier, so as we know that the energy stored will be half CV square and where our energy stored, that is V equals W equals to half d dot ds whole, this we have studied, or half epsilon mod of E square. That is basically you have to integrate it mod of over the surface E square ds. So okay, so it will be the energy stored. Now for region 1, what we did? Okay, and so we have applied for the region 1. So for region 1, so our E was, that is electric field in the region, was del of grad 1, grad V. It was minus del, that is Ax del by del x plus Ay del by del y into V1. So into V1. So V1 was our V naught plus 2 V naught B into Y. And if we sort out all these things, so we got V naught over B A Y. This we did in the last class. So this was the voltage, the electric field in the region 1. And after that we can calculate the, and that is energy stored in the region 1. That is energy per unit length in region 1 will be what we have to integrate over the region 1. We integrate, that is W1 will be half d dot f ds, or equal to half epsilon integrate over the region, that is x equals to 0 to x equals to 0 to W by 2, x equals to 0 to W by 2, and y equals to minus b by 2 to 0, and that will be mod of E square. So that is 4 V naught square over B square dy dx. If you solve this integral, we will have E epsilon over W over 2B into V naught square. So this will be the energy stored in the region 1. Now we need to find out what is the energy stored in the region 2. For region 2, we know the what would be the voltage V2 of xy. So we have expressed, it was we have expressed the voltage. It was, so summation n equals to 1 3, that is 5 to infinity an sine of n pi y by b, then sine of hyperbolic n pi a by 2 minus x over b. This was the voltage, and from the voltage in the region 2 we can find out the electric field. So electric E2 will be minus grad V2. So we will have Ax del by del x plus Ay del by del y V2. So we will have, if you substitute the value of V2 from this equation in here, so what we are going to have, we will be having Ax Ex2 Ex plus Ax plus Ay Ey. So you can find out the what are the electric field component associated with the x direction, and what are the electric field component with the y direction. So we will have E2 will be E2 or Ex will be minus del V2 over del x. So we have to differentiate with respect to x here. We have to differentiate with respect to x. So what we will have? We will have summation n equals to 1, 3, 5 to infinity n pi by b an cos hyperbolic n pi by b a by 2 minus x sine of n pi by y by b. Similarly, ey will be minus del v2 by del y. So you can differentiate this v2 with respect to y minus. We'll have summation that is minus n equals to 1, 3, 5 infinity n pi by b. Okay, sine an sine hyperbolic n pi b a by 2 minus x into cos of n pi y by b. So we will, from here we will get E2. E2 will be our minus E2 will be ax ex plus ay ey. E2 is known. Now once E2 is known, after that we can find out the what is the electric field associated, what is the energy stored associated with the, that is energy per unit length in region 2 will be, so we'll have W2 will be half epsilon, that will be half epsilon integral over the region ex square plus ey square dx dy. So if we substitute it, so W2 will be our half epsilon. So what we'll have, y equals to minus b by 2 to 0 and x equals to w by 2 to x equals to w by 2 to a by 2 in the region to a by 2, and summation, we will have summations, that is summation, because it will be squared, every term will be squared, so it has to be multiplied by, means let's say everything is, it has to be multiplied by everything, means okay, every series has to multiply it by this, so it will have m n m, so you'll have m pi square over b square a m a n, and summation means and the multiplication of all the terms, and we will have, and that is I will write sine hyperbolic m pi by b a by 2 minus x sine hyperbolic n pi by b a by 2 minus x. So this is the first, that is ex square. In ex square we'll have, that is cos of term, and the cos of term, that is sine term, hyperbolic term, so it will be multiplied, it will have m and n term both. Similarly for cos also, that is cos of m pi y by b, cos of, it is just squaring, we have squared the term, squaring is squaring the two series term, n pi y by b. So this was for the ex, plus for the, similarly we will have for the ey, that is cos hyperbolic m pi by b a by 2 minus x cos hyperbolic n pi by b a by 2 minus x into sine hyperbolic, sorry, sine m pi y by b into sine n pi y by b whole, and after that we'll have dx dy. So we need to find out the energy stored. To find out the energy stored, so what we'll have, we need to solve this integral. So here we have used the double summation, which to when you will multiply the EX with EX. Okay. Then you will have double integration. And due to the orthogonality, so we will have all the terms will be 0. That is, if m and n are not same, so it will become a square. Otherwise, all are will become 0. So that due to the due to the orthogonality condition. Okay, orthogonality condition of sine cos, cosine. So all the terms vanish except when m equals to n due to the orthogonality condition. So what we are going to have here, so we will have, so okay, so W2, if you solve it, half epsilon summation n equals to odd, it is 135 n square pi square an square b square, and this will give you a b by 2. Okay, so this will be, if we integrate the y term, this will give me b by 2, this will give me b by 2, these two will give me b by 2. So we'll have b by 2 okay, and b by 2, and that is x, we'll have integration only in x, we'll have sine hyperbolic square m pi by n, we are dealing, so n pi by b a by 2 minus x plus cosine hyperbolic square n pi by b a by 2 minus x whole term dx. Okay, so we will have only these two. Now our problem reduces, we have to solve only this integral. And so if we solve this integral, so we can you can solve this integral. So if you solve this integral, I will write the answer. So that is half epsilon n equals to odd, that is 135. We will have n square pi square an square over 4b. Half will come, that is 2 will come from here, 2 will come from here. So 4b, and yeah, and this term will give us b by 2. So will give us b by n pi. So please try to solve this integral using the hyperbolic property, using the hyperbolic identities. Okay, please try to solve this integral. Solve it. So solve it. Solve this integral, and this integral will give us b by n pi into cos hyperbolic n pi by 2b a minus w sine hyperbolic n pi by 2b a minus w. So this will be our W2. And further, so if we substitute, so this will be our W2. If you substitute the value of an was, what was our an? An was something, it was dependent on, yeah, an an was something sin hyperbolic minus b. So substitute the value of an. Substitute the value of an. So your W2 will become n equals to odd to infinite. Okay, so we'll have 8 epsilon v naught square over n cube pi cube cot hyperbolic n pi by 2b a minus w. So this will be the energy stored in the region 2. Okay. So now, we want to find out the total energy stored in the strip line. So the total energy stored in the strip line, the total energy is stored in the strip line will be, so it is for the one quadrant. So total energy, let's say W will be 4 times of W1 plus W2. And by using we know that and W equals to also half C V naught square, because this is the voltage we have given. This is the voltage. So by using this expression, so this will give us C equals to 2W over V naught square. So substitute the value of W. So C will be, the capacitance per unit length will be 8 times 8 of V naught square over W1 plus W2. This will be the capacitance. So this will be the capacitance here. Okay. Now substitute the value of W1 and W2. If we substitute the value of W1 and W2, finally we will have the capacitance will be epsilon 4 omega 4W by B plus 64 pi cube summation n equals to odd to infinite 1 over n cube or hyperbolic n pi b by, it will be 2 also, 2 a minus w. So this will be the this will be the capacitance. This will be the capacitance per unit length. And we need to find out, as it was asked, so this we found out the capacitance. By using the capacitance, we can find out what would be the characteristic impedance by using the expression. So the characteristic impedance can be found out by characteristic impedance of a transmission line. The characteristics impedance of this transmission line will be, it is lossless. We are assuming to be lossless. So Z0 equals to under root mu epsilon. So this is discussed in the BTech class, Z0, and substitute the value of this mu epsilon in terms of C. We will have mu r epsilon r into this will be small c and into C. This, so small c is the speed of light. Speed of light. You can see the capacitance per unit length. So if we substitute it, so what we are going to have? We are going to have Z0 equals to 120 pi, because this value is 120 pi. 120 pi over under root of epsilon r 4w 4w by b 64 pi cube summation n equals to odd to infinite 1 over n cube cot hyperbolic n pi by 2b a minus w. 2 I have a question whether 2 is there not there. I will check it, then I will inform you. So this will be the characteristic impedance of this transmission line. So in this way you can find out the characteristic impedance of a transmission line. So this is we have means you can solve the characteristic impedance. So why we want to calculate the electrical max, that is we want to calculate the voltage, so to calculate its characteristic impedance. So, and by knowing its characteristic impedance, we can design the components further. So this was one problem. So we will give you some more problem based on this, like this. Okay, so we will move further. Okay, so we have seen few problems. We have seen the problem, how to use, when to use this expansion method. We will solve few more problems to check means when we can use the series expansion method. Now write down the one problem. So problem is that solve the two-dimensional problem. Solve the two-dimensional problem, that is del square V equals to, that is Poisson's equation is given, that is del square V equals to rho by epsilon, where that is till now we have seen the Laplace equation, but in the Poisson's equation this rho s is given by, it depends on the space coordinate, that is x minus x into y minus 1 nanocoulomb per meter square, subject to the condition, that is v of xy, v of x0 equals to 0, v of xb equals to v naught, v of 0y equals to 0, v of a y equals to 0. So this problem can be, we need to solve the Poisson's equation given by this relation, that is del square V equals to rho, and where rho s was given, it was given in terms of space coordinates, so we need to solve it. So if we draw the coordinate system, it will be x, it will be y. So what we are going to have, so we need to solve this. Basically this problem is governed by this differential equation, that is this is your PDE problem. We need to solve it, and here this is x equals to 0, this is x equals to a, y equals to 0, y equals to b. We need to solve, and the voltages at x equals x, y equals at this one, this is 0, this is 0, this is 0, and we have only this one, this will be v naught, this is not 0, that is x equal at v of x at y equals to b is v naught. So we need to solve this one here, that is del square v equals to minus rho s by epsilon. So how to solve this one? Okay, so this is, we can see it is not having the particular integral, means particular, so we cannot find out the particular solution. Why? That is del square v equals to minus rho s. We cannot find out the particular solution because of this term. So if del square v equals to 0, we can straightforward apply the either series expansion, we can straightforward apply this one. You can straightforward apply the whatever the variable separation method and solve this problem. We already solved this problem, but because of this term, we are not able to solve it. So for this, we will use the series expansion method. So if you see here, in this problem, there are two source terms. That is two source terms. First is your V naught. Second one is minus rho s by, that is rho s by epsilon naught. So two source term means you can get the your V of xy depends upon this V naught and rho of s. Rho of s. So rho of s was your x minus x into y minus 1. So how to tackle this problem? So we can solve this problem by taking one source term at a time. So let us take and apply the superposition theorem to get the entire voltage at in the region. So for the first one, for the first source, so we can apply, okay, we can apply the superposition theorem, superposition, to get the voltage V of xy in the region, in the defined region. Okay, so yeah, so first we'll tackle with V naught. So if we tackle with V naught, so what we will have, so this rho s will be 0, that will be rho s will be 0. We assumed to be 0. Then what we are going to have, so it will become, our life will become very easy. So we will have, let us say that the voltage corresponding to this one will be V1 of xy. So what we will solve? V1 of xy. So we need to solve this del square V1 equals to 0, subject to the boundary condition, that is V1 x equals to 0, then V1 of xb equals to b naught, and then V1 of 0 y equals to 0, and V1 of a y equals to 0. And so this will be one problem, and this problem we have already solved it. So straightforward, we can write the expressions. So if we have already solved it, so we can write the expression. Second problem, straightforward, we can write the expression of V1 of xy. Second is, if we consider the second term, that is rho s by epsilon naught, this source term, okay, then our V naught will be 0. That is, V naught will be 0 in this case. So we will have this del square V. So our problem will reduce to del square V equals to minus rho s by epsilon naught, where rho s will be your x into y minus 1, rho x into y minus 1, and subject to the boundary condition. So here the boundary condition will change. Subject, it will be V2, subject to boundary condition, that is V2 of x0 equals to 0, V2 of xb equals to 0, V2 of 0y equals to 0, V2 of a y equals to 0. Means at all the periphery of this one, voltage will be 0, and we will have only this source term, that is our rho s by epsilon naught. We need to solve this one. So we will have, for this we'll have, and we can use this series expansion method to solve this problem. So series expansion method can be used to solve the problem. Okay, and let us say that solution will be V of xy, V2 of xy, and so final solution will be final solution will be your v of xy will be v1 of xy plus v2 of xy, the superposition of these two. We will have the final, this will be our final solution. Now to solve it, so let us move further and solve it. So we will solve the expression. So we'll just, because we already know the expression for the first one, so we will write it for the first section. So for the first problem, okay, for the first problem we already know that v1 of xy, that will be 4 v naught over pi summation n equals to 135 to infinity sine of n pi x by a sine hyperbolic n pi y by a over sine of hyperbolic sine hyperbolic n pi b by a. This we have already solved it. And also we want to show, means you can also check it, use the solution, you can use the series extension method to get this expression. Series extension, please try to do it. So this will be a homework. Okay, try to find this vxy v1 using series extension method. You will get the series same result, series expansion method. Okay, so you will get this is the A. Now for the second problem, that is, we'll have another source term, that is rho s by epsilon naught. So we have the differential equation minus v2 equals to rho s by epsilon naught. So we need to solve this equation. So how to solve this one? So we have seen the okay, so how to solve it? So we can write the expression in this way. So we have solved this in the three-dimensional. So let us solve it. So let us say that v2 of xy, will be of the form of m equals to 1 to infinity, n equals to 1 to infinity, a of mn sine n pi x by a sine n m sine, so it will be m first n pi y by b. The reason why we have chosen sine term here, because at the periphery, at the boundaries, this term will go and it will satisfy the boundary condition. This is true also here. So that is why you must choose this type of function such a way this satisfies the boundary condition. So this sine m pi x by a and sine n pi y by b satisfies the boundary conditions. Okay, so this, both of them satisfies the boundary condition. So this will be, which boundary condition will be satisfied by this one? So we'll have, that is, we will have v2 of 0 y equals to 0, v2 of a y equals to 0. This boundary condition will be satisfied by this one. And for this, v2 of x0 will be 0 and v2 of xb will be 0. So by looking into it, you can say that it is satisfying both boundary conditions. Now our aim is to find out the an. An can be find out. So we can write down an. So what we need to do? We need to just substitute. So we did it for the three-dimensional, that is, so we have del square V2 over del x square plus del square V2 over del x y2 equals to minus, uh, let us say that this will be fx, okay, fxy, and after that we will substitute the value of fxy. It is fxy. So we did it for the three-dimensional case, that is, we were having here plus del square V2 over del z square in the three-dimensional. That is, we have solved the Poisson's equation inside a cube that we solved. We have solved this Poisson's equation. Now we will have, it will be of the similar behavior, nothing great here. Just you have to substitute the substitute the value of V2 here, and try to find out solve it further. So if we try to find out, so we will write A of mn will be 4 of AB m pi by A whole square n pi by B whole square inverse, and it will be 0 to B, 0 to A, fx y sine of n, that is m pi x by A sine of n pi y by B dx dy. If you look into the that is A, m, and p in the Poisson's equation in the cube, everything it will be remain same. It was 8 by ABC, and here p pi by C, and 0 to C, and here that is sine p pi z by C was there, and dz was there. Additional term were introduced. Now by using this one, so let us say that since our fx, that is rho of s, so rho of s is equals to fy minus 1 over epsilon. It was minus here, so it was it was this expression, that is this nano coulomb per meter square. Since we have this term, then what is going to happen? Substitute this fx value here and try to solve this integral. If you substitute this integral, try to solve it. Let us solve this integral. So we will have, that is 0 to B, 0 to A, fx y sine of m pi x by A, then sine of n pi y by B dx dy. Okay, fx substitute after substitution of x, so it will be, it will be 10 to the power minus, since it is nano coulomb, we'll multiply 10 to the power 9 over epsilon naught. Then let us take the atom, so we'll have x into sine of m pi x by A dx, and 0 to B y minus 1 sine of n pi y by B dy. Okay, so now if we solve it, so you can solve this term separate, this term separate, and you will get the expression 10 to the power minus 9. So it will be, epsilon will be 10 to the power minus 9 over 36 pi. And I have not solved this expression. If you solve this expression, you will get minus a square minus a, I'm writing the expression, cos of m pi over m pi, and for this expression we will get minus b square cos of n pi over n pi plus b over n pi cos n pi minus 1. Okay, so this is integral can be easily solved, nothing great here. So if we further reduced it, so what we are going to have, we'll have 36 pi minus 1 raised to power m plus n a square b square over mn pi square and over 1 minus 1 over b, 1 over b, 1 minus 1 to the power n, and this will be our final expression. This will be the integral. And why we where for cos n pi we have substituted, that is cos of n pi will be minus 1 to the power n. Okay, now you substitute the value of this integral, integral in the main expression. So your an will become a of mn will be m pi by a whole square n pi by b whole square inverse, and this an term, this expression into further it will be, that will be minus 1 is power m, that is m plus n 144 ab over m n pi 1 minus 1 over b 1 minus 1 is power n. Okay, so this will be our amn. Okay, now so since we have calculated the values of v1 and v2, so our v1 and v2 will file so complete solution. So the complete solution will be of the form of v1 of xy equals to 4 v0 over pi summation, that is for v1, n equals to 135 to infinity sine of n pi x by a sine hyperbolic n pi y by b over n sine hyperbolic n pi b by, this is a, b by a, plus this was our v1 of xy, plus we will have summation n equals to 1 to infinity, n equals to 1 to infinity, a of mn sine of n pi, that is m pi x by a sine of n pi y by b. So this will be our v2 of xy, and amn has been calculated above. So amn has been calculated above. So in this way we can solve this problem. Means we can try to find out. What we did, we have as we have the problem, so we have broken down into problem into two smaller problems and try to solve it.